I want you've got, and it might be hard to handle. Like a flame that burns a candle. The candle feeds the flame. Yeah, yeah, what I got, full stock of thoughts and dreams that scatter. And you pull them all together. And I can't explain. Oh yeah, well, you make my dreams come true.
Hi everyone, welcome to another week for Chrome 861. This week I'm going to actually kind of cover 2 weeks because it makes sense to talk about cluster analysis and principal components analysis together because they're both data reduction methods. Cluster analysis focuses on the sort of reducing data to cluster individuals together. Principal components analysis is a type of exploratory factor analysis that instead looks at grouping or reducing the number of variables in an analysis, so putting variables together as opposed to putting individuals together. So I'm going to begin with describing cluster analysis. The idea here is where we're going to create homogeneous groups from a heterogeneous sample, or at least that's what we would have in mind, to minimize within group variation. So within our clusters, we're going to have a lot of similarity amongst individuals. And then we're going to also maximize between group differences. So we will see a lot of variation between cluster number 1 and cluster number 2, cluster number 2 and 3, and cluster number 3 and cluster number 1. So Garson shows how you can also use cluster analysis to cluster variables together as opposed to individuals. But I think that factor analyses are a little bit more traditional in terms of how we go about clustering variables or grouping together variables rather than persons. So we'll focus on the principal components analysis method as kind of an introduction to factor analysis. But for right now, we're going to focus on cluster analysis. I'll give you a little bit of a conceptual example about how the algorithm works when we think about clustering individuals together. So in this conceptual example, imagine that we have 6 individuals and we wanted to cluster them according to color preferences or the shades of colors that they felt represented them. And so we can see 1 through 6. We can have some colors that seem similar than others. And what the cluster analysis algorithm will do is it begins by identifying the 2 most similar individuals in the sample. And maybe this is based on a single variable like color, or maybe in your analyses you've selected 10 variables, and basically the analysis will run through each of those 10 variables and identify individuals, the two individuals who are most similar to one another on those 10 variables, so considering all 10 of those variables. So those first 2 individuals will form the first cluster in the analysis. And then the analysis will then identify the 3rd and 4th individual in the sample that are most similar together, and the comparison will be made. The analysis will ask, is the 3rd individual that we've identified more similar to A, the 4th individual that we've identified, or B, the 2nd individual that we identified in that original cluster? So would they be better suited in that original cluster that we identified, or should we be creating a brand new cluster with individuals 3 and individuals 4? So that's the question that the algorithm is asking. And if it's sort of focusing on the latter, then we would now have a 2nd cluster. So that's the general idea of how cluster analysis is going to work. Sometimes cluster analysis is just used as a purely data reduction method. So if you have a lot of variables in your analysis, maybe to reduce those number of variables, you will cluster them together, and maybe you've got a 3 cluster solution, so you can take those 10 variables and you've essentially reduced them down to 3. To me, a more useful implementation of cluster analysis would be if there are particular theories in your field that have this idea that there are qualitatively distinct groups according to these particular variables. So we can identify individuals whose profiles on these 10 variables are actually in fact different. And then we can begin to look at one of 2 questions. So we might want to look at whether there's a particular profile that's most informative of your outcome of interest. So do our clusters predict our dependent variable? Or maybe our clusters are our dependent variable. We want to look at, for example, whether different risk factors or different other theoretical constructs of interest are more informative of one particular profile than another. Either way, this is what we would refer to when talking about validating clusters. Essentially, we want to ask 4 questions when validating our clusters. We want to think about whether the clusters seem to be meaningful, like on face value plus criterion validity, so looking at which particular items are most strongly associated with which particular cluster is kind of the first step. Like, do these clusters seem to theoretically be relevant to us? Then we want to look at whether they're distinct enough to warrant the designation as clusters. So is group 1 substantively different from group 2, and group 2 is substantively different from group 3. We also want to verify that the clusters we've identified are actually going to be large enough in terms of sample size. Like SPSS or whatever software program you're using is going to force the algorithm to identify a solution. And sometimes these solutions will not really be ideal or practical. If you have a sample of 100 individuals and one cluster is defined by only 5% of your sample, there isn't much that you can do with this cluster. It's kind of hard to validate it when you only have 5 individuals in this particular cluster. And so the last question is that we want to cross-validate our clusters. So something, for example, we would do is look at convergent validity or predictive validity of the clusters. So basically, for the first question, it's up to you to know the literature that you're working in. I'm not going to be able to necessarily tell you whether your clusters make sense or not if it's not my sort of substantive research area. It's up to you to kind of make this conceptual decision of, do these clusters seem relevant to what past literature has reported on? The other thing that we need to, again, make sure of is that these clusters are actually substantively different. If they're not, what's the point of doing the cluster analysis? And I'll show you an example today of where cluster analysis might not be particularly useful or really adding anything new to our analyses. We don't want to just validate the clusters according to like face value. We want to take an extra step and look at whether these clusters are related to other particular variables in a way anticipated by theory or what we would expect based on what past research has said. Garson goes over 3 types of cluster analysis. I'm going to talk about each of these 3 conceptually, and I'm going to do an example in SPSS of using 2-step cluster analysis. The first type of cluster analysis that Garson discusses is what's referred to as hierarchical cluster analysis. And it's referred to as hierarchical because sometimes we have clusters within clusters. So this is sometimes what we see in machine learning with decision tree algorithms, where we'll see here's one general cluster, but we have 2 subtypes within this cluster. HCA is primarily used with interval level data. So when you're doing this type of analysis, I'm going to kind of recommend against it, and I'll explain why in a bit, but you need to make sure that the distance measure, so the algorithm that you select to kind of create these clusters, coincides with the level of measurement of your variables. We would use Euclidean distance for interval level variables. We would use chi-square analysis for counts. And we would also use Euclidean distance for binary variables. I don't recommend performing this analysis when you have nominal variables with 3 or more categories, like if you had a measure of race and you had individuals who were indigenous, white, and black. This wouldn't really work because there's no real appropriate distance measure for this type of nominal variable. HCA is really only reserved for small samples. And if you have a larger sample, there are more preferable options. So HCA is kind of more like a last resort. Different interval level variables can be on different scales. You might have one variable measuring income, another variable measuring age. So obviously very clearly different scales. So you need to make sure that these variables are standardized. Usually in SPSS, for any type of cluster analysis you're doing, there'll actually be a default option to standardize your variables. So usually this isn't something you need to worry about. You can just do it right in the analysis. HCA is not sensitive to the order of your data, which is a good thing. This statement might not make much sense, but it's going to make a little bit more sense when I begin to describe k-means cluster analysis. K-means cluster analysis requires the researcher to pre-specify the number of clusters that you want the algorithm to produce. So there are a couple options here. The first is that you can start with like a one group solution and then add what we would say k plus 1, where k equals the number of groups. So you go from a one group solution to a two group solution, kind of compare the fit of those two. Then maybe you would go from a two group solution to a three group solution and compare the fit of the two versus the three group. And basically you would end your procedure once you've identified that the increase in the number of solutions doesn't result in an improvement in kind of the model fit or the validity or like conceptual validity of the model. The second option would be to actually run your analysis using HCA. Find out what HCA identifies as the appropriate number of clusters. And then you can force this number of clusters in k-means. You can do the same thing if you wanted to run two-step. Two-step will identify for you the right number of clusters, and then you could force the solution in k-means. You wouldn't really do this though, because in my opinion, two-step is actually like kind of like an improvement on k-means. So you would just kind of go with the two-step analysis to begin with. But I'd say that the k-means cluster analysis is more appropriate than HCA if you have a larger data set. It tends to produce equal size clusters, which in my opinion is not a good thing. So if you had 100 individuals and 3 clusters was the solution that you forced to be specified, you'd probably find like 33, 33, 34 within the 3 different clusters. So very simple sample size, similar sample size. And the reason why I don't think this is a good thing, because it kind of, we might not expect groups to be of equal size. If we go back to, for example, Moffat's description, Terry Moffat's description of adolescence limited versus life course persistent offending, these might be 2 clusters of individuals. But the AL group is supposed to make up about 90% of all individuals. So you wouldn't want your cluster analysis trying to divide the sample into 50-50 when you know in theory the ratio is more like 90-10. K-means relies on Euclidean distance, meaning that you should only be using interval level data and dichotomous data. So in the last slide, I talked about a strength of HCA is that it's not dependent on the order of your data. In k-means cluster analysis, the order of your data, so how your data are sorted, sort of influences the algorithm's selection of who is going to go into which cluster. And if your data are sorted in a non-random way, you could almost be forcing particular solutions to be identified, or well, you're forcing the number of solutions, but the nature of those groups could be dictated by how your data are sorted. So what you want to do in SPSS, for example, is create a random number generator so that each case or each participant in your sample gets a random number. Then you can just sort those random numbers in ascending order, descending order, doesn't really matter because they're ultimately random. And then you can use that order to run your analysis. So all you have to do is go into SPSS, go to transform, and then in the drop-down menu, there's an option for the creation of a random number generator. I keep mentioning Euclidean distance as basically the way in which individuals are clustered together, and I think I'll maybe explain what that actually means. Euclidean distance is calculated by plotting 2 individuals. So very simple, like just imagine a scatter plot. You've got your x-axis, you've got your y-axis. The x-axis represents one variable, the y-axis represents another variable. And you're going to take 2 individuals and you're going to plot their score. So here's where they would fall on the x-axis and then up or down along the y-axis. So you've done this for the 2 individuals. then you'd basically calculate the difference between each case on the x-axis, the difference between each case on the y-axis. And then essentially the distance between the two is calculated as the square root of the sum of the squares of the x difference plus the y difference. So the sum of the squares, you're squaring the difference between x and the difference between y, because if you were to add the difference between x and y, but y is negative, you'd actually reduce the magnitude of difference. So if on x the difference was plus 2, but on y the difference was negative 2, if you added them together, you'd get 0. But if you square plus 2 and negative 2, you got 4 plus 4. So you look at the sum of, so the square root of 8 would be your calculation or your answer to the question of Euclidean distance. Two-step clustering is the example that I'm going to go through in class today. And it's also, I think, probably the type of cluster analysis that most students who choose to use cluster analysis will want to use. So two-step clustering creates pre-clusters and then uses hierarchical cluster analysis basically to cluster the pre-clusters. So it's kind of like a special case of hierarchical cluster analysis. And it's fairly robust because it allows for the inclusion of both categorical and interval data. So there will be a drop-down box in SPSS, and you can indicate whether a particular variable should be included as an interval level variable or a nominal non-dichotomous variable. Like k-means analysis and like other analyses, you need to make sure that your variables are on the same scale, which means you would standardize your variables if necessary. Each CA requires basically the analysis to identify the appropriate number of clusters. K-means requires you to pre-specify the appropriate number of clusters. Two-step allows you to choose between which of those two options you want. I recommend that you allow the appropriate number of clusters to emerge from the data. So we have some different basically indicators of model fit, and we use those to help identify which cluster solution is the most appropriate. Just like with k-means, we can use a random number generator to help order our data. When we get into SPSS, you'll see that there are different ways or different options that we can select in order to tell the analysis how to identify the appropriate number of clusters. And one of the main sort of criteria, or two different options you can select, is the difference between Bayesian information criteria or Aikiki information criteria. Values closer to 0 indicate improvements in model fit. So the closer to 0 your BIC value or AIC value is, the better the model fit actually is. BIC, kind of think of it as adjusted R squared, and AIC as R squared. They're not looking at percent of variance explained, but the reason why they're similar is that BIC penalizes the model for complexity. So I think it's more ideal. It's going to sort of favor a little bit more of a parsimonious model. That way we don't have, for example, a cluster with 3 individuals in it. If you rely on AIC values, you're more prone to having a greater number of clusters with small numbers of individuals within those clusters. In addition to BIC values, One of the things that we'll also look at when interpreting model fit is the ratio of distance measures. And this is again something that's just a checkbox to select in SPSS. The larger the distance we see, basically it shows the bigger the change in the ratio of BIC values. So we're seeing that as we move from a 2-group solution to a 3-group solution, if we see a large ratio of distance measure, it means that not only did BIC get closer to 0, it got quite a bit closer to 0 based on the ratio of the BIC values for a 2-group solution to a 3-group solution. So that's basically all we need to run through in terms of the conceptual descriptions of each of those 3 cluster analyses. Now we'll jump into SPSS, and I'll use the pathways to desistance data to examine a 2-step clustering analysis using YPI Youth Psychopathic Traits Inventory data. We'll look at 10 different features of psychopathy and whether they help us identify different qualitatively distinct clusters of individuals according to their features of psychopathy. Okay, so I'm going to give for the class a little example of how we would run a cluster analysis. I'm going to take a look at features of psychopathy to basically examine whether there are subtypes of persons with strong features of psychopathy, and then examine whether these clusters are informative of some external outcomes, in this case offending outcomes, and this helps establish the external validity of the clusters that we're examining. So we've got the pathways to desistance study data set here, and from the second wave, the 6-month wave, we have 10 variables from the YPI that are tapping into different features of psychopathy. So you can see here we have things like dishonesty, grandiosity, and lying representing interpersonal features. We have affective features here, and we have some behavioral features there. So we're going to include each of these in a cluster analysis. If you did need to standardize the variables, you would just create z-scores from those particular variables. So if you go up to descriptives, you can enter your variables into the variable box, and then you just save standardized values as variables, and then you would get standardized values for each of the new variables that you included in that variable box. We're just going to go up to Analyze, and then we're going to have to scroll down. We're going to go to Classify. I've talked about k-means cluster and hierarchical cluster analysis. For this one, I'm going to be focusing on the 2-step cluster analysis. And so remember, in this case, like I could have done maybe k-means, but one of the reasons why I wanted to show students this example is because it might be more applicable to what you'll be using in your papers or assignments, because it allows for mixed variables. So you can see here that our level of measurement can be different for different variables. I could enter categorical variables, and I could enter continuous variables. I could include these in the same analysis. So we'll take these 10 variables here, and I'll include them in the continuous variable box. Down here you see distance measures, and you see log likelihood and Euclidean. Euclidean would be reserved for if we had dichotomous data. The 2-step analysis performs better if these interval level variables or these continuous variables are normally distributed, just like in any other type of analysis, but we don't need them to be normally distributed. So I mentioned you could standardize variables just through the descriptives, but the analysis will actually default to standardizing the variables for you, which is what you want unless all variables are on the same scale. The next thing that we're going to do is just click on options, and there are a couple of things that you can do. If you click on noise handling, it's useful if you have only small clusters forming. So if you get really small, like say 5 clusters, and one cluster keeps showing up with only like 3 people in it, for example, you can use noise handling to help deal with that issue. And basically the way that noise handling works is that it actually clusters outliers. So things that don't really fit, it will cluster them into their own group. I prefer to not really use this. What's more important is that you click this output box here, and you're going to want to check off pivot tables and create cluster membership variable. You really need to do this one so that you'll actually get in your save variables a variable that will indicate which cluster a particular person in your sample actually belongs to. So we can do that, and we can paste our syntax, or we can just here I'll hit OK. All right, so we get our output here, and what we're interested in a number of things, but we're going to start with BIC values. So in this case, we're looking at the BIC values that will be closest to 0. And so in this case, we're looking for effectively the smallest number. So the number of clusters with the smallest number would be here, where we have 5362.154. But another thing that we want to take into consideration is the parsimony of the model. A high number of clusters is going to, especially if we have a smaller sample size, is going to make things a little complex. So another element that we're interested in is the ratio of distance measures, and SPSS tends to favor this over BIC values. So if you look here for the ratio of distance measures, we're effectively just looking for the largest number, and here it's shown as the largest number for that 3 cluster solution. So SPSS is kind of faced with this discrepancy. They could be selecting the 6-group solution, or they could be selecting a 3-group solution. And if you look down here at cluster distribution, you can see that clearly they went with that 3-group solution. What the ratio of distance measures basically means is that it implies a longer distance between the clusters and thus more distinct clusters. Again, we don't just want to have individuals within one particular cluster that are highly similar to one another, but also kind of similar to individuals in a second cluster. What we want to see is that within a, let's say, cluster number 1, these individuals are highly similar to one another, but they're also highly different from the individuals in cluster 2 and in cluster 3. And so the ratio of distance measures is helpful for identifying this particular interest. Another thing that we have here is you can see the BIC change and the ratio of BIC change. If the ratio of BIC changes is kind of small, then basically SPSS, the algorithm, is going to decide that there is not a suitable trade-off between fit and parsimony. So yeah, we can get to these smaller and smaller ratios, and you can tell where the cutoff is because it goes from positive, that's number 6, it's 0.002, and then negative for 7-group solution of negative 0.007. But we see, like, moving from a 5-group solution to a 6-group solution is a ratio change of 0.002, so very, very minuscule. Therefore, what SPSS is looking for is trying to maximize the ratio of BIC changes. So you can see moving from a 2 to a 3-group solution is quite substantial compared to moving from a 3-group solution to a 4-group solution. So we've got this high ratio of distance measures, a high ratio of BIC changes, so it kind of makes sense that SPSS has basically landed on this 3-group solution. Now that we've basically got our 3-group solution, it's time to begin to interpret what we're seeing. So if you look at model summary and you double click, we're going to have this model viewer box. It's going to give us some interesting information. So your main interests are in cluster quality, and you want it to be of at least fair. So we can see in this little box here that it meets that fair quality. We want to look at the percentage of the sample in each cluster and verify, for example, we wouldn't really want to have fewer than 5% of sample members in one particular cluster. So in this case, we see a 3-group solution, and there's one that's almost half the sample, and then 2 others that are relatively evenly split across the remaining 2 groups. The next thing that we're going to be interested in is predictor importance. It's going to tell us which features of psychopathy are most helpful in distinguishing these 3 different clusters. So under the view box, if we go from cluster sizes, we can select instead predictor importance. And then we can see at the top here the magnitude of importance in helping to basically identify which features of psychopathy are most important to assigning an individual to a particular cluster. At the very bottom, it tells us the least important is callous and the most important is manipulative. And then you can see sort of the magnitude of these in particular items or traits for features of psychopathy. Manipulation, dishonest charm, and remorselessness essentially being the most important variables in our model in terms of influencing whether an individual would be assigned to group 1 or group 2 or group 3. We also need to interpret the nature of clusters. So what do they actually look like? How are they distinct? What are the ways that help define or distinguish the three clusters? Again, this can all be done in this window. Now we're going to go down to View and select Model Summary. And we're going to move from Model Summary to Clusters. And then we can see the variables in terms of their average score across the three clusters. You can also see up the top the importance of that predictor to that particular cluster. So this is where our interpretation begins. So we can look at group 3 and manipulation. Remember, it's that most important variable in the model. We can see that its average value for group 3 is 14.43. If we hover over dishonest charm, we can see that the mean is 14.86. We can compare that to, for group 2, it's only 6.57, and for group 1, 10.34. Now we're beginning to see a pattern. For cluster number 3, we tend to see these individuals having the highest score. So for example, if we look at lying, it's a mean of 12, higher than for group 2 and for group 3. Same thing when looking at thrill seeking, comparing group 2 and to group 3. Same thing when we get down to grandiosity. Okay, so now we've found like our high scoring group. These individuals tend to score high across every single feature of psychopathy. The next question is, do we have any distinctive differences between cluster 1 and cluster 2? So as like a heads up, very often we get very boring differences where the cluster analysis is supposed to be useful to help identify qualitative differences between our different clusters. However, what we might often find are simply these kind of boring quantitative differences where we have a group that scores high, a group that scores medium, and a group that scores low. And then like when you think about it, so if we have this high scoring group and a medium scoring group and a low scoring group, then why not just use the interval level variable itself instead of creating these kind of like nominal categories? So what we're looking for when we're examining group 1 and group 2 is whether there are situations or scenarios where group 1 scores higher than group 2 on certain features of psychopathy, and group 2 scores higher than group 1 on other features of psychopathy. So we can take a look at that here. So right now we're seeing evidence that group 3 is high, group 1 is medium because you can see manipulation 9.66 versus for group 2 6.09. So let's do a little bit of a further check. We've only looked at one particular variable, that manipulation variable. Let's see if this holds up across each of the features of psychopathy that we're examining. Is group 2 always scoring lower than group 1? So if you look at dishonest charm, 657 compared to 1034, 682 to 1035, 8 to 12, 5 to 9, 10 to 13, 8 to 11, 8 to 10, 7 to 10, 11 to 11. So basically, what we're seeing here is that we have three clusters. Cluster number 3 is characterized by the highest features of psychopathy. Group 1 or cluster 1 is characterized by more moderate features of psychopathy. And group 2 is characterized by lower levels of features of psychopathy. So not especially interesting in this particular case. That's okay. This is what's going to probably happen for your own analyses as well. You might just see kind of like high, moderate, low groups. For the purposes of this course, it's totally fine. So if you wanted to take like a closer look at how the different clusters broke down compared to the average for the sample, if you go to cell distribution and you click on any particular item, you can see that particular score or the distribution of scores on that particular item for the particular cluster that you're clicking on. So right now I've clicked on group 2, but I could move over to group 3 and you can see that darker shade of red, that more prominent red, is the distribution of manipulation scores for those who fit into cluster 3. So let's say that these were the clusters that we decided to retain. Now, if you look at the very bottom of your data set, you have this new variable, TSC 4, 5, 2, 3, but I might want to kind of rename it YPI clusters, YPI standing for the Youth Psychopathic Traits Inventory, and then I might want to give them specific values. So if you'll recall, group 1 was moderate, group 2 was low, and group 3 was high. So now it'll kind of assist us with interpretation, which is the next thing that we need to do. So for example, I would want to verify whether my clusters were in line with what I might have a theoretical expectation about. So in this case, I'm just going to do a simple ANOVA analysis where I'm going to use the clusters as my factor variable, the categories of interest, and then I'll look at versatility score, offending versatility, go into options, descriptives, homogeneity of variance, Brown-Forsyth in case Levine's is violated, post hoc, Bonferroni, Tamhani. This will be PTSD for you, going back to like week 2 or 3 of the class. Can hit OK. And then we can begin to look at whether there seems to be sort of what we would expect or things are in line with our theoretical expectation. And they are. So we can see that the highest scoring group averages the highest level of offending versatility compared to the low and the moderate is higher than the low. We can explore this a little bit further, so we can see that Levine's has been violated, so we would be focusing on Brown-Forsyth. We can see that the model is significant. The next question is the post hoc analysis. We would flip down to Tamhani, and we can see that moderate scored significantly higher on levels of offending versatility compared to low. The inverse was true when we compared moderate to high. If we look down here, we can see that high scored significantly higher or averaged significantly higher levels of offending versatility compared to the low scoring group. So again, we found evidence of external validity. I would say that the clusters themselves aren't all that unique or interesting because, like, why not just do a correlation analysis? For example, if I went up to correlate, went to bivariate, I could look at something like the YPI total score, or I could look at its factor scores, and then I could look at the offending versatility variable right here, hit OK, and then I can see that each of the factor scores for the interpersonal domain, the affective domain, and the behavioral domain are significantly correlated with offending versatility. So basically, did we learn anything unique from creating that cluster analysis? And my personal opinion is no. If you kind of feel the same way for your own cluster analysis, for your paper, if you find that talking about the cluster analysis kind of interrupts the flow of your analysis and doesn't really add anything to it, it's okay to just put it in appendix and then explain why. So in the text, in the body of your paper, explain why your cluster analysis didn't really add to any unique findings. So you might actually just keep it in the appendix so that it won't interrupt the flow of your paper. Okay, so another thing that we'll talk about is what if the cluster solution that SPSS forced you to retain is one that you don't really agree with. So let's just say, for example, that we had a particular theoretical perspective that was suggesting that there were 4 subtypes of psychopathy. And so we might actually want to retain this 4 cluster solution, but SPSS is forcing us to retain this 3 group solution. We can actually force the analysis to select that 4 group solution. All we do is we go back into our cluster analysis, and under number of clusters, we can specify a fixed number. So we'd say, okay, we're going to force you to spew out a 4 group solution. And then we can see the cluster quality went down a little bit, but it's still okay. So then we would maybe want to have a look at our clusters and see if we see something different than just like high, medium, low. So in this case, we've got our high group looks to be group number 4, and I'd say that's true. Let's then look at group number 3. That seems to be kind of like our moderate group. So then the question becomes, is there any evidence that group 3 scores higher on particular features of psychopathy, but either group 2 or group 1 score higher than group 3 on other features of psychopathy. And unfortunately, the answer pretty much is no. Like, there's dishonest charm is 10 for group 1, it's 10 for group 3, 11 for group 3 on remorselessness, lower for group 1, 11-1 for group 1 on impulsivity, and for group 3, 13-4-6. So basically, we can just see quantitative differences. Group 4 is highest, group 3 is maybe moderately high, group 1 is just moderate, and group 2 is low. So we don't really get anything unique. The moving from a 3-group solution to a 4-group solution doesn't help us identify like qualitatively distinct groups of individuals based on their features of psychopathy, which to be honest is actually exactly what I would have expected based on the research that has been done on features of psychopathy to this point. So I would kind of just go with that 3-group solution, or I would just, if I was doing my CRIM 861 term paper, I would in the text talk about how I did the cluster solution, how I arrived at my 3-group solution, but that the examination of the 3-group solution did not really yield anything of theoretical substance. So it's available and in the appendix, but you'll just continue to look at the raw scores, or like treat the variable as that interval level variable like it was all along. So that's it for cluster analysis. Now that we've kind of figured out how we cluster individuals, the next set of analyses are focusing on how we cluster variables, or how we group together variables. So we'll talk a little bit about factor analysis. Principal components analysis is a type of exploratory factor analysis. If you're interested in this type of thing, when you take CRIM 863, you should have a look at confirmatory factor analysis and structural equation modeling, which basically build on these exploratory methods. So principal components analysis is another type of data reduction technique, but we need to again think about like, why are we trying to reduce our data? We need to go back to the idea of, or start with the idea of what a latent variable actually is, or a latent construct. One, I think, very easily understandable latent construct is aggression. Aggression isn't something that we physically see. Like, there are different behaviors that we think underscore what aggression looks like. If we saw someone punch somebody, if we saw somebody push somebody, yelling at somebody, we could think about different types of, for example, relational aggression or passive aggressive behaviors. These could be different types of aggression. So we can look at all these different types and wonder whether there are particular components of aggression or different facets of aggression that seem to go together. So are there types of like very physical aggression that all sort of correlate strongly together? And then there are examples of relational aggression or passive aggressive behavior that also kind of correlate strongly together. This is what we're looking at when we're doing exploratory factor analysis. We might have a theoretical idea, or maybe we just want to begin to look through our data and allow the analysis to produce particular factors of types of aggression and how an individual might score on physical aggression versus relational aggression, or covert forms of aggression that aren't actually like direct towards a particular individual. So if you're deciding between cluster analysis and principal components analysis for your term paper, what would lead you to the decision to select PCA? Basically, you'd be looking at whether you have like a bunch of different variables that you think might be indicators of the same latent construct, or maybe 10 variables and you think 5 are highly correlated together and they represent one part of a latent construct, and then another 5 variables that all go together and represent another part of a latent construct. So we basically are thinking about variables that we think may be really strongly correlated with one another. When we were doing cluster analysis, we weren't necessarily thinking about the variables being correlated together. We were really thinking about, do individuals seem similar to one another? Here we're looking at the relationship among the variables in our analysis. Often they're coming from a scale. So a scale is designed to measure a particular latent construct, whether it could be like emotions or self-identity or maturation, which we'll take a look at in our empirical example today. If we find that all of our variables load onto one single factor, it's actually good. It justifies us adding all of these different items or variables together to create a single variable representing our overarching scale, our overarching latent construct of interest. So it helps us keep things simple. So if you find that your components analysis only produces one factor, like, don't be dismayed. Having a univariate scale with just one construct can actually be quite useful in terms of parsimony. Principal components analysis can actually also be an answer to issues with multicollinearity. So if you have variance inflation factor values that are high, we've talked about interaction terms in the past as ways to deal with this. Another way to deal with it is to run a principal components analysis, because the factor scores on each component are literally uncorrelated with each other. The analysis produces it so that the correlation equals 0. For cluster analysis, most of our assumptions kind of revolve around levels of measurement, making sure that our data are not ordered in a particular way. When it comes to principal components analysis, we have a few more assumptions to address, and a lot of them are similar to linear regression, though the violation of assumptions in principal components analysis is less severe than the violation of those same assumptions in linear regression. On the topic of linear regression, the relationship between variables in the particular components should be linear. So we should see, if we take variable 1 and variable 2, a 1 unit increase in variable 1 should have the same increase in variable 2, regardless of the level of variable 1 that we're looking at. So whether we're looking at lower scores, medium scores, high scores. PCA can help deal with multicollinearity, but at the same time, it's one of those things to try to avoid if possible. Another assumption that I think is fairly important, but it's more conceptual, so there's nothing that you can look for in the analysis, is that you've included all relevant variables that would be forming this theoretical factor of interest. So if we were looking at identity, but we excluded, for example, how somebody thinks about them in terms of their physical appearance, or how they think about themselves in terms of their prosociality, this could actually impact what the analysis uncovers. So if we've excluded these relevant variables, then the right number of factors or the nature of the factor might be different from if we had included all relevant variables. The last thing that we'll touch on in terms of assumptions is that your variables that you include in the PCA should be normally distributed, and so they should be continuous. You can get away with ordinal level variables if the range is large enough to sort of help you identify a normal distribution. The rotation option in SPSS for looking at the principal components analysis helps essentially clean up your components to make them more easily interpretable. The unrotated solution is the most mathematically efficient solution, but it's not necessarily very interpretable. So you'll want to use what's called the Varimax rotation, which is a type of orthogonal rotation that makes it so that the factors are entirely uncorrelated and therefore as different as possible. So factor 1 and factor 2 will be perfectly uncorrelated. If you find that your PCA is identifying like an unreasonably high number of factors, try the Cordimax rotation. And if you're having difficulty with the interpretation of the solution, you could try the Equimax rotation. And if you're having difficulty with the interpretation of the components, like they just don't really seem to make theoretical sense, you could try the Oblinin rotation. SPSS output will produce a KMO and Bartlett score. The KMO score is giving you an indication almost of effect size, where the closer to 1, the better. If the value of KMO is less than 0.5, then the set of variables that you've chosen seem to be inadequate in producing a factor solution, probably because your variables simply are just not correlated enough. So one of the things you might want to do even before you run your analysis is to actually enter all of your variables into a correlation analysis and see whether at least some of them are quite strongly correlated with one another. The Bartlett values that you get test the null hypothesis that all correlations are 0. So obviously we want to reject the Bartlett test. So if the Bartlett test is significant, then good news. Communalities tell us basically about the extent to which a particular variable contributes to the underlying component or the underlying factor. A higher score means the variable is making a greater contribution to the overall factor or component. We want to kind of go with a threshold of 0.5 or greater. But if you think the variable is important theoretically or to your model, then it makes sense to keep it even if it does have a low communality score. And if you decide to drop that particular variable from your principal components analysis, that doesn't mean you have to drop it from your model altogether. If you're going to use those components to predict your outcome of interest, keep those components, but that variable that you dropped, add it into your regression model as just its own variable. KMO is one indicator of effect size. Variance explained is another thing that we can look at, and this is represented by eigenvalues in SPSS. And the eigenvalue in SPSS must be greater than 1 for that factor to form. So whereas KMO is kind of like an indication of the overall model, the eigenvalues are informative of the value of or the importance of a individual factor that's been identified. So we could look at a 3-component solution, and KMO would tell us about the overall solution, and then eigenvalues would tell us about the value of each of those 3 factors on their own. Eigenvalue comes from the word eigen, which basically just means the sum of variance amongst those variables. The higher the variance value is, the more those variables move together, aka the more correlated they are with one another. Another term that you'll see is sums of squared loadings. And remember, sum of squares isn't some brand new term. You've seen this before when we're looking at our line of best fit. It's trying to minimize our sum of squares, those squared distances that we just talked about as well with cluster analysis. So the cumulative percent is your explained variance, and you want that number to be higher as well. What you'll sometimes see is the K1 rule. Basically, it means that a group, aka K, will not be retained, or that factor will not be retained unless its eigenvalue is greater than 1. Eigenvalues are one method or approach for identifying the appropriate number of components in our PCA. So each component with an eigenvalue of greater than 1 would be retained. Another approach is to look at the screw plot. It's a little bit more subjective. Basically, it's looking for the first break, the most dramatic break, and which one to choose. So it's looking kind of for an elbow-shaped pattern. It's easier, we'll just jump into the slide here so you can kind of see it more closely. We're looking for the biggest break between 2 components. This is just another way to validate the solution that you've had. So let's say that you had a components analysis that revealed 3 components, but the eigenvalue for the 3rd component was like 1.00, like right on the dot. So maybe you check the scree plot and it shows a clear break between the 1st and 2nd component, which would give you an indication that, okay, maybe I do want to select instead a 2-component solution. So you could go back into your analysis and force a 2-component solution even though the third component did have an eigenvalue of greater than 1 or was 1, but it was just so close, it was so borderline, it just made more sense to you, based on theory, based on past research, to go with a 2-component solution instead. If you do get discrepancy, so the scree plot is saying 2 groups and K1 is saying 3 groups, SPSS will default to the K1 rule. So then you just need to go back into SPSS, and under extraction, you can look at the fixed number of factors, and then you can force it to be a 3-factor solution or force it to be a 2-factor solution, whatever it was that this scree plot was telling you to retain. What you'll also want to do, just like with cluster analysis, you want to save those cluster variables, those clustering groups. You'll want to save the factor score. So each subject basically has a score that merges their answers together on each variable from each factor to basically give an indication of an individual score on each factor or each component that your analysis identified. You can then use these factor scores to predict your outcome of interest, or maybe the factor scores are your dependent variable. This makes the most sense when these components seem distinct and seem theoretically meaningful. When it comes to principal components analysis, there are a lot of different things to take into consideration when looking at the validity of your solution. So this is just kind of a review of what to think about. So just like cluster analysis, think about comprehensibility and face value validity. Do they make sense? Does it make sense that these variables all correlate together on this particular factor and these particular variables correlate on this particular factor? Like, do those variables being together make sense? Can you look at those 5 variables and find a common thread? Like, can you name that component? Is it easy to name the component? When you name that component, does that kind of give a clear indication of the variables associated with the component? For K1, the Kaiser criterion, you're looking for eigenvalues that are 1 or greater, or above 1. For the scree plot, you're looking at that elbow break, the first dramatic break in clusters or components is where you would select that number of components. Another thing that I didn't mention, but it was really important, never retain a factor or component with less than 3 variables. It basically doesn't allow us to create a scale. Generally speaking, when we're creating scales, we can't have a scale defined only by 2 items or 2 variables. All right, so now we'll just jump into SPSS and go through an example of a principal components analysis using different indicators of maturation from the Pathways to Desistance study dataset. Alright, so I'm going to show you how you do a principal components analysis. And one of the things that you want to think about before you start running your analysis is the direction of your data. So as an example, I'm going to be giving a run through of a principal components analysis looking at different components of maturation. So all of these components of maturation that you can see highlighted here indicate that higher scores on these particular measures indicate greater levels of maturation. So more self-regulation, a more positive sense of self-identity, a stronger work orientation, the ability to show greater consideration of others. All these things are kind of positive aspects of maturation, indicating that a person has more maturation. We have this other one up here called moral disengagement. Basically is like justifying criminal attitudes, denying harm to victims, and so on. And higher scores on the moral disengagement variable indicate that this individual is like more antisocial. For the purposes of your actual PCA, you could include this variable and it won't impact the validity or the reliability of your analysis. But I find just personally it's easier to interpret things when the particular variable, when all the particular variables in your analysis are coded in the same direction. So what would you do here? You've got this moral disengagement scale and it ranges from 1 to 32. So you could do a couple of things. You could let 32 equal 1 and 1 equal 32, then 2 would equal 31, and 31 would equal 2, and so on and so on. But an easier thing to do is just go up to transform, go to compute variable, and I could do, it's called S0 moral, I could just call it moral recode, or I think it's more accurate, moral disengagement, and it's going to be the add_inv. Why am I calling it the add_inv? Well, it's taking the additive inverse of the variable. So all I have to do is multiply this old variable of moral disengagement by -1, and now my new variable has made 32 now equal -2. So now higher scores on the moral disengagement scale actually indicate that the individual has less moral disengagement. Like the higher the score, so 0 being the highest, the less morally disengaged the individual is. I'm not sure if that's going to be helpful or applicable in your case. I'm actually, just to keep things simple, I'm not even going to look at moral disengagement for the purposes of this analysis, just to keep things more straightforward. Another thing that you can do before your analysis is just have a quick peek to see if your measures that you're including in the principal components analysis actually correlate with one another. If there's like zero correlation between any of your variables, then it doesn't make much sense to actually examine them. However, as you can see here for our example, basically every single measure that we're looking at is significantly correlated with all other variables in our principal components analysis. So we have about, I think, maybe 8 to 10 different variables here measuring different aspects of maturation according to Michael Rock's integrated maturation theory. If you're interested in this particular theory, I'll pop up an article that I've written regarding this theory that you can check out. But our question here is, okay, so is maturation a univariate phenomenon? If it's a univariate phenomenon, we would get one single component, and each of these different items would all load onto that one single component. Or maybe we will begin to see different aspects of maturation. So maybe we'll see some that are relating to psychosocial maturation. For example, temperance is referring to impulse control and suppression of aggression. And maybe that is more strongly related to resistance to peer influence. So if you're less impulsive, you're better able to resist peers. Maybe things like work orientation and expectations about work and thinking about the future, maybe those will be particularly strongly connected to one another. We don't necessarily know right away. We can check out the correlation matrix and maybe get some hints at that, look for which variables are most strongly correlated with one another. But that requires us to kind of look at one variable by one variable by one variable. These are just bivariate analyses. If we want to look at all of these variables together in a principal components analysis, we're just going to go up to Analyze, then we're going to go to Dimension Reduction, and we're going to select Factor. In our factor analysis, and remember, I have here all interval level variables. That's what you should be using in your own analysis, or dichotomous variables, but you shouldn't have nominal or categorical variables in there. To start with, at the top, we'll go to descriptives, and I also recommend selecting univariate descriptives. The correlation matrix, we've already looked at this, but if you wanted to look at it again, you can just click off coefficients there. Then, as I mentioned in lecture, there are a couple of things that you want to look at. One is the KMO, and then you can look at Bartlett's test of sphericity. We're good to go there. We can hit continue. And in terms of the extraction, remember this can be helpful for the interpretation of the actual, or the number of components that best describe the variables. So we can select that scree plot option there. We don't want to change anything here. That K1 rule is what we're seeing here. Based on eigenvalues, it's basically saying that our component must have an eigenvalue greater than 1 to be retained. So if a 3-component solution, that third component is 1.1 eigenvalues, but if we add a fourth component, the fourth component is 0.8 eigenvalues, then the analysis is going to retain that 3-component solution. If your scree plot is telling you something different from eigenvalues and you wanted to check out what your scree plot is suggesting, you would switch to fixed number of factors and then enter the number of factors or components that your scree plot is recommending. But we're going to start here with the K1 rule based on eigenvalues. The rotation helps us with the interpretation of the nature of the components. So we're going to select, as mentioned in lecture, the Varimax rotation. And then for scores, we want to save as variables. And I recommend just the default save as regression variables so you can include them in your regression analyses. We haven't looked at options, but there's nothing here that you need to take a look at. So we can just go cancel and we can begin to run our analysis. The first couple pieces of output aren't really giving me any new information that I couldn't have got from my univariate analyses by looking at descriptive statistics and my bivariate analyses by looking at the correlation matrix. This correlation matrix might look slightly different from the one that we've looked at above because this correlation matrix is based on complete data for each of the 9 variables that we're looking at in this particular analysis. To look at the correlation between the Walden self-regulation scale and the future orientation inventory, it's not looking at all available data for variable 1 and variable 2. It's actually looking at all the correlation between variable 1 and variable 2 based on individuals that had complete data for all 9 variables. So here we can see that for self-regulation, its correlation with consideration of others is 0.307. If you look up here, you can see that's 0.303. So if you're wondering why the correlation coefficient changes, it's because here you can see the sample size is 1,351 people. If you look down here, only 1,340 people were actually included in the principal components analysis. So these 1,340 people were those that had complete data on all 9 items. That's why we see slightly different correlation coefficients. When we're looking at KMO and Bartlett's test, these are 2 different analyses. The KMO test is where we're looking for kind of like an effect size indicator that ranges from 0 to 1, where the closer to 1 the better, and anything less than 0.5 is basically saying that the set of variables that we've chosen to examine are inadequate in producing a factor solution. So here we can conclude that the KMO sampling adequacy test statistic is sufficient, it's greater than 0.5. And we can also look at the Bartlett's test of sphericity, kind of given the same idea as KMO. It's basically testing the null hypothesis that the correlations are 0. And here it's significant, so we're rejecting the null hypothesis. We're saying that the correlation coefficients are not 0. And therefore, this is again what we want. We have correlations among our variables, and this will help produce a factor solution. We can't find a factor solution if all of our variables are uncorrelated. When we're looking at communalities, we typically are using a value of around 0.5 to justify dropping a particular item. However, if we think that that item might be theoretically irrelevant, we might still choose to include it in the components analysis. Alternatively, one of the things that we might do is, for example, here we can see that resistance to peer influence, the communality of 0.262 is very low. So we might drop it from the components analysis, but retain it in our regression model because we still think that it's an important variable tapping into maturation that we want to include to predict our dependent variable or outcome of interest. The total variance explained output is that K1 test, so we're looking for eigenvalues that are greater than 1. So here we have component 1 with an eigenvalue of 3, component 2 with an eigenvalue of over 1, and component 3 has an eigenvalue of less than 1, so that's where we stop. It is recommending to us a 2-component solution. So eigenvalues are recommending to us a 2-component solution, and if we take a look at the scree plot, I think we continue to see evidence for a 2-component solution. So as I mentioned, we're kind of looking for when does the elbow shape appear. And to me, we can see it go from the 2-component solution to the 3-component solution. After the 3-component solution, the arm is fairly straight. So as you can see, the y-axis is just plotting the eigenvalues. The exact same thing that you see in the total variance explained table is what you see in these component numbers. Component number on the x-axis, the eigenvalue on the y-axis. So basically what you can see is that once we move from that 2 to 3 group solution, we don't see too much of a change. So we would stop at where the break started, which means we would retain the 2 group solution. So we've seen a substantial drop between 2 and 3. 3 falls below the line of 1. And thereafter, we're always going to continue to see lower eigenvalues. We will see 2 matrices that give us an indication of how the different variables load onto the 2 components. The one that you want to look at is the rotated component matrix. That's where we selected that Varimax rotation. And this can help us look basically at which particular variables were associated with the first component and which particular variables were associated with the second component. So for example, if we look starting with the first component, we can see that self-reliance, identity, work orientation, and resistance to peer influence all seem to load onto that first component. The loadings are greater than 0.5. For the second component, we've got the Walden self-regulation scale, the future orientation inventory, expectations about family, work, and the law, criminal justice system. And then if we look down at the bottom, we can see temperance and consideration of others also load strongly onto this second component. Now we can also see that for temperance, its factor loading is only 0.418, and for resistance to peer influence, its factor loading is only 0.507. And if we look up at the communalities, these 2 in particular, resistance to peer influence and temperance, were very low. So I would almost step back, and I might avoid bothering to interpret this rotated components matrix because I know that I'm probably going to remove those 2 items from the model. What I want to do is investigate what would happen if I drop those 2 items whose communalities were quite low. So what happens if I drop resistance to peer influence and temperance? So very simple. All I have to do is go back into my principal components analysis, and I'm going to drop resistance to peer influence and temperance, rerun my model, and now KMO hasn't really changed. Bartlett's test of sphericity is still significant. Extraction values of greater than 0.5, but 0.4 is fairly borderline. I've still got those 2 components based on the K1 test, and the scree plot once again kind of looks identical to the one that we were looking at up here. Virtually no difference. So I would be retaining a 2 component solution. And then I'm going to go back to my rotated component matrix, and looking at component 1, it's comprised of self-reliance, identity, work orientation, and then on component 2, we have the Walden, future orientation, expectations about work, family, and the law, and consideration of others. So now here's where you need to know the variables that you're looking at and the analysis that you're wanting to do, or the theory that you're working from, and you want to give your components names. You want to look at their interpretability. So what I think I would say here is that factor 1 is kind of looking at individual maturation, so ability to rely on themselves, how they feel about themselves, and kind of their work ethic, all kind of individual based aspects of maturation. Then maybe F2 I could call social maturation, which is the ability to regulate your behavior around others, think about the future and how your behavior is going to impact others. Obviously, work, family, and the law, that has a lot to do with social maturation. Consideration of others, also about sort of social maturation. So that's what I might name or label my different components. So once you run your analysis, when you click those save variables, you'll be able to save for each individual their score on your component 1, which we labeled individual maturation, and then component 2, which we labeled social maturation. So you could even do something like relabel them like individual underscore maturation and social underscore maturation, just to make things easier. Remember, we talked about how the factor scores will be uncorrelated, and so this is something that could be used to help deal with multicollinearity. Just to prove it to you that I'm not lying, we could run a correlation analysis between factor score 1 and factor score 2, and you will see that they are perfectly not correlated. So their correlation coefficient is 0.000. So now we could enter them into a regression analysis. Let's just say we're going to do a very simple regression, linear regression. Let's see what we've got down here. We'll enter our factor scores. Let's enter PCL to control for. We've got our offending versatility variable. Let's just keep it gang involvement so that we've got a categorical variable in there as well. We can run our linear regression analysis. I'm not going to worry about assumptions or anything like that, but just show you this is what we would do if we wanted to look at the prediction of maturation against offending. So we can see that individual maturation was not significant. However, social maturation, what we see is that a 1 unit increase in the level of social maturation was associated with a 0.165 unit decrease in our measure of the log of offending versatility, or whatever it happens to be. That's just a demonstration of what you can do with your principal components. Some things that you might wonder about when you're running your principal components analysis, so these random frequently asked questions. One is whether having one component is a bad thing, and it's absolutely not a bad thing. Basically means you can put all of those variables together. It's very parsimonious. That one factor score kind of provides a comprehensive description of all individuals' scores across those variables that you've chosen to include in the components analysis. Garson will talk about R mode, which can be confusing. This is just your classic data setup where you have your cases in the rows. So here you can see case ID 54335 follows along the rows, and our variables follow along the columns. I don't know why it's called R mode, but that's how it is. There are a lot of different types of factor analysis. If you go up to dimension reduction factor, if we go to, what is it? Scores? No, it's extraction. You could select a bunch of different ones. We've also talked about exploratory factor analyses. There's confirmatory factor analysis. There is structural equation modeling. Don't worry about any of that for now. All you need to know for this class is principal components analysis. We will step back to the rotated component matrix here. Ideally, your factor loadings will be greater than 0.7, and your cross loadings should be below 0.3 or 0.4. So what does a cross loading mean? For component 1, self-reliance belongs on component 1. The cross-loading is its factor loading for component 2. So self-reliance 0.896, it belongs on component 1. We want to make sure that the cross-loading is below 0.3 or at least below 0.4. So I talked about exploratory factor analysis and principal components analysis. But principal components analysis is also kind of a type of exploratory analysis. So what's the difference? With principal components analysis, the goal is to maximize the total variance explained among all variables, which you can see up here in this particular table, where the cumulative percent explained by your two factors for all of the variables is 61.6%. For factor analysis, it's not so much interested in trying to explain the total variance amongst all variables, but rather focusing on variance within a specific factor. So these three variables load onto this specific factor, and for exploratory factor analysis is seeking to maximize the variance explained within that one particular factor. Another thing that I should mention, it's not on the slide, maybe I mentioned it earlier, is that you do not want to retain a component where only two or fewer variables load onto that component. So each component that you have should have three variables that load onto it. I mentioned this in the synchronous lecture, but just want to repeat it. Like if your whether we're talking about your principal components analysis or your cluster analysis, if they don't seem to make much theoretical sense, looking at your rotated component matrix and you're like, I just don't see any meaningful relationship between the variables that load on component 1 or on component 2, these 4 variables just do not seem to go together whatsoever. Like, I get the factor loadings are high for all of them, but putting them together, I don't see like a clear label for this component. It's okay. You can talk in your results section about how the component analysis or the cluster analysis did not provide substantial or like informative information about the relationship among these variables. But they are available in an appendix. So then put your analysis in an appendix, talk about it, interpret it in your appendix so I can see that you know what you're looking for, but at least it won't interrupt the flow of your paper. So hopefully this has been helpful. Hopefully it's not too overwhelming to put these 2 analyses together, but just remember, take your time. You have 2 weeks to sort of review this video. You might want to look at cluster analysis 1 week and component analysis the next week. All right, so we're done. This was the last asynchronous lecture for this course. Hopefully this class and all other lectures have been helpful to you somewhat. We'll see you in the synchronous class later in the upcoming weeks. Take care, everybody.